Okay, last section of chapter 6. Now it's putting a lot of this work into the exponential model. Remember, we have this standard exponential model where A represents the start of our graph or our equation. And that start means when x is 0, whenever this value is 0. B is going to be what we multiply by each time. Exponential means multiply. So here's the equation that we're going to use for all exponentials. Now, a couple things to know. When you multiply by a number bigger than 1, when the b is bigger than 1, like when you multiply by 2 or 1.5 or 17, that's going to make numbers get bigger and bigger and bigger, so we're going to call that growth. If you multiply by a b value like 1/2, a number that's smaller than 1, but we want to talk about numbers bigger than 0. So if you multiply by 0.7 or 1/2 or 1/12 or 0.2, multiplying by those numbers like 1/2 is going to make it smaller. So that's going to be called decay. So here's our basic equation that you're familiar with by now. So I want to do a couple examples here right out of your homework. This one is on page 377, problem number 5. What's happening here is obviously as time passes, we have a cooling off of this hot water. So the water starts out warm and then is put in the freezer and starts to cool off. What we want to do is they tell us that this decreases exponentially. So what we want to do is to write this exponential equation in the form y equals mx plus b. First question asks find ratios. Remember, ratio just means fraction, and that's going to be what we multiply by each time. So that is going to be the b value that we find. To find the ratios, what we want is to multiply. What do we multiply to get this? Now, obviously, since it's going down, the temperature's decreasing each time, we should be multiplying by a number that's smaller than 1. So here's how I'm going to go about finding these ratios. All I do is to find what I multiply by, I'm going to use the inverse. I'm going to divide. So the 45 divided by the 47 gives me 0.96. So what I multiply to get from here to here is times 0.96. To find out a consistent value, I want to find all of them. What did I multiply to get to 45 to get to 43? I just divide it, and that's times 0.91. And then I just did several of these, and you should do all of them. This multiplies by 0.97. And I continue down here to 40. How we got to 40 here is times 0.96. I skipped a few here. You do them all. To multiply this last one is 0.97. And then here I got times 0.95. So we get all these ratios. You find these other ratios as to what we multiply by. So here, obviously it changes a little bit because it's not going to be exact, temperature fluctuations or whatever. But what we want to do is find out what is the average ratio. So it says find the mean, which is average. You average them all out, and I got about 0.96 when we do the averaging. Now, I expect to see your work on how to find average. Remember, you add all the values and then divide by how many there are. It looks like there should be 10 averages here. So add them all up and divide by that, and you should get around 0.96. And like we said, that's causing a decay. So 0.96 is less than 1. And what this means is 96% of our temperature is being left behind. So we get 96% of our temperature every minute. Or another way to look at that is to think of this as we start with the 100% of our temperature, all of our temperature, and then we lose 4% each time. So a common way to write this would be instead of multiplying by 0.96, it's 100% minus the loss of 4% to get our multiplier. I, of course, prefer using the 0.96, but understand what that means is that we have a loss of 4% of the temperature. What remains, this is always going to be the amount that remains behind. Here, it's our remaining temperature, which is our multiplier of 0.96. Then it continues to ask us to write an equation. To write an equation here, we have the y equals a b to the x. Now, where a is the start value, b is our multiplier, x is how many stages that we've gone through. Here, the stages are being represented in minutes. And y is going to be our temperature. So here's our x-axis and our y-axis. So y is going to be the temperature that we have. So here we write it where a being the start value when x was 0, a is 47. We can see right in our table here. 0.96, that multiplier, is what we found our average multiplier to be. So here we can write an equation that represents this freezing water and what its temperature should be at any given time. So we can check the temperature after 5 minutes, after 8 minutes, after 10 minutes, and see what the temperature is. Then it's asked to graph it. Be careful when you graph, make sure that we expect even pieces here. Our scale has to be even. So if you start at 0, 1, 2, 3 minutes for our time, and then make sure your scale is even here. It looks like the highest temperature is 47, so maybe you want to go up to 50, break it up by 5s, break it up by 1s, whatever. Make sure that you have even markings here. What you should see is what's called an exponential decay. It should be a curve that decreases. The temperature should go down as the time moves forward. So it's a curve that decays like this. Then it asks us to take this equation, and we want to find out when the temperature is 5 degrees. So we write exactly our equation down, and we find the temperature at 5 degrees. Now the way for us to solve this, in Algebra 2, right now I'm dealing with my Algebra 2 students, and we have an algebraic way to solve this using logarithms. Right now you don't know about logarithms, so the only way for you to do it is to test different numbers. Now obviously it's got to be, if we look at this, we're going to get down to 5 degrees centigrade. Way down here in my table is going to be a lot more than 10 minutes it should take. So it should take more than 10 minutes. So what you have to do is test different times. So if you test 10, well, you ought to be in the 30-minute range. But if you test maybe 15 minutes, put 16 minutes in here, 29 minutes, and then solve this way by just plugging numbers in and testing. So there's that one example. I want to try another example with you that I have prepared here. On the worksheet, 6.7, well, your worksheet, it asks us to write an equation when they tell us the start cost of this vehicle is $26,400 and it depreciates, or there is a loss of 8%. Remember, what we want in our equation is what remains behind. So our B value is we start with 100%, we lose 8, so our B value is going to be 92%. Now remember, we always write our value as a decimal equivalent, so the percent changes to a decimal of 0.92. So when we write this equation, we start off with the A equals B to the X, where A is the start cost at year 0, when the time is 0, when we first bought it, $26,400, and our B value is this multiplier of what remains. So 92% of the value remains behind. Hopefully that's enough for you to get a good start on this.